So let's see how we can get these two sort of famous conceptual conclusions that occur inside of special relativity. The first one I'll show you is called time dilation, and the second one I'll show you is called length contraction. The point is, if you have observers that have a relative speed between them, so they are moving differently, but they are both inertial observers. We have to be careful. So, but if you have these two observers that have a relative motion between them, they will measure different amounts of time to occur between two events, the same two events that occur in nature, and they'll also measure different distances between two events. And the way that you can get these conceptual phenomenon to the way you can see them happen is by doing a thought experiment with what I refer to as a light clock. And this light clock is specifically going to be held at rest in the inertial frame called O prime. So let me show you what this light clock looks like. And it amounts to being something of a comic strip. So the light clock has two parts. It has the mirror. So you know what mirrors do to light. And it also has a piece of electronics that I'm going to abbreviate as the SDT. So the SDT is for source, detector, and timer. And the idea is you can send out a little light signal. So this is a little piece of light, and it's going to travel across the gap, hit the mirror, and reflect and come back down. So this will be, say, when the light signal is emitted, and then a little bit of time later. So here is the source, detector, timer, and here is the mirror. So a little bit of time later, the light signal has gotten to the mirror and is being reflected. So this is a little string of light, or like a little light wave, or however conceptually you think of light, or it could be a little particle of light like a photon. But anyhow, this light hits the mirror and starts its trip back. So a little bit of time even later, here is the mirror again, and here is the source, detector, timer. And the little photon is on its return trip to become detected. And you can imagine that this thought experiment light clock could measure the time, right? I could keep track of how much time this took. So that's a little timer. Okay, so in this thought experiment, this light clock is actually going to be at rest in O prime. So the light clock is at rest in O prime. And what's more is, I forgot to mention this, but the distance is going to be designated by L. So L equals distance that light travels outbound and inbound, right? So the outbound is, say, between here and here, and then the inbound is from here to all the way back to the detector. Okay, so that's called L. All right. So the gist, right, the whole point is to do a thought experiment where the special thing in special relativity is that this light signal, regardless of who's watching it, O or O prime, is going to travel at a fixed speed c. So O is going to see the light travel along its path at the speed c, and O prime is also going to see the light travel from its origin through the reflection back to where it's detected, also at the speed c. And this is an Einstein postulate. And the idea is when we invoke this postulate, we're going to get time dilation, and we're also going to get length contraction, but with two different experiments. So these are going to be two different thought experiments. That is, no single thought experiment is going to give us both length contraction and time dilation. We have to have two different ones, and it would be good, as you watch this video, if you can keep track of what is the difference. As a sort of to prepare you, that the difference is direction. It's how this light clock is oriented. So in our first thought experiment, in O prime, we have a stationary light clock. Yeah, and it's sort of aimed upwards, so the light is going to be emitted here, travel across, reflect, and be detected there. In O, though, this light clock has an orientation such that when the event happens such that the light begins its emission, the light clock is traveling towards the right. And so the idea is the light clock is oriented transverse, that is perpendicular, to the relative motion between O and O prime. In a sense, the position of the clock is the location of O prime because the clock is stationary in O prime. So O prime is moving towards the right inside of O. You could view it this way. So here, in O prime, it's quite simple. You have an emission, a reflection, and a detection, right? So the emission and the detection happen at the same place. So emission and detection happen at the same place in O prime. But here, what's interesting, and this is really the important difference, in O, the emission and the detection happen at two different places. And these two different places are further apart the faster that O prime moves in O, or the faster the relative motion is between these two frames. Okay, so over here, we can do some really quick kinematics. We can say that there is a certain amount of time that passes, or that this timer is going to measure. It's a timer that happens to be stationary in O prime, so this timer is actually a clock in O prime. It's one clock in O prime, and the delta t that's going to happen between emission and detection, well, the time that it takes to travel the distance twice L, right? You go out L and then you travel L again on the inbound. If you divide by the speed at which the light travels, that gives you the amount of time delta t prime, right? So twice L over c. So the game here in O is to get an expression for delta t. But before we do any math, notice that light in O travels further, right? So it travels further, but at the same speed, c. And so you can conclude immediately that O will see in its clocks that it takes more time. Right? We didn't have to do any math. If you look at what the light path actually needs to do, is it starts here, but as it travels towards the mirror, it also travels sideways. So really the path of the light is this diagonal line. This is the path of the light. But the problem is as it travels this path, according to Einstein's postulate for the constancy of the speed of light, it travels this longer path with the very same speed. It's if we were maybe talking about sound waves or something, we'd have to fix the speed. But in this case, this is the big deal that makes everything sort of like very different from what you expect in classical physics, non-modern physics. What's weird is O is still going to notice that the light travels along this longer path at the very same speed that O prime sees, right? So O prime uses the speed c to travel the distance 2l, but over here in O is going to see the light travel longer than the distance twice l, right? The distance that this light has to travel is twice the distance of whatever this sort of hypotenuse is. So that's what we need to figure out, is how long is this distance in O, right, from here to there. So the way you figure that out is you say that the timer, right, that is the entire light clock apparatus is traveling towards the right at the relative speed between O prime and O, because the clock is standing still in O prime, right? So so this light clock is at rest in O prime. So the light clock is traveling at the speed of O prime within O. So it's traveling towards the right at the speed u. So what we'll do is we're going to do this. We're going to say that there is an amount of time, delta t, and I'm going to split it, put it over 2, because we have to wait that same amount of time again. So on the outbound to the reflection is an amount of time delta t over 2, and on the inbound from the reflection to the detection is another amount of time delta t over 2, and the distance is going to be the square root of the speed u times delta t over 2. So this, if you look at this right here is the sideways distance traveled during the time delta t that we don't know the value of delta t. But we do know that half the time is spent getting to the reflection and the other half the time is spent just undoing the very same distance, right? Or redoing the same distance. So the path there is traveled sideways at u delta t over 2 squared. And then vertically, though, this is interesting, the vertical distance is just L, right? That's the size of the clock, or the distance between the source and the mirror and the detector. Okay, so that vertical distance goes like this. And so you can see that I just used the Pythagorean theorem. And D is the hypotenuse. So we can immediately write down that delta T over 2, right? That's the amount of time it takes, say, from emission to reflection, is equal to the distance traveled divided by the speed at which you travel it. So the distance traveled is this square root stuff. So it's U delta T over 2 quantity squared plus L squared. That's the distance traveled. And then you divide by the speed, and this is the crazy thing, the postulate, Einstein's postulate of relativity is for the constancy of speed of light. So this just gets divided by the speed c. It's the same speed as in as O prime would measure, right? So what this gets you, if you go and you follow your nose, you can get to a place, right? So you have to use this and you use this, and what you're looking to do is to relate delta t prime and delta t. So your goal is relate delta t prime and delta t, and what you're going to get is that delta t is equal to 1 over the square root of 1 minus u squared over c squared times delta t prime. This is what you're going to get. And this is called the time dilation formula. Yeah, so if you do this, which honestly is just some algebra, and you may find that the thing you can relate between these two sort of equations is actually L. So L is something that you can relate. So if, for example, if you took this equation here and you solved for L, and you took this equation up here and also solved for L, what you would find, and then set those L's equal to each other, is you'd get this after some algebra. So this is the time dilation formula. I need to bring up a really important point about the time dilation formula. In particular, this is this formula where the amount of time measured by a rest frame O is equal to 1 over the square root 1 minus u squared over c squared times the amount of time measured by the frame O prime. So this time dilation formula. So this is a really quite an important point. Delta t prime, the thing that sits right here, must be the so-called proper time. So how do you determine if a time duration is a proper time? The way you determine this, so proper time is measured by 1 clock. So so this proper time, and it's important to notice that we're not talking about a particular moment in time. What we're talking about is a time duration, right? So there's you push the start button on your stopwatch, and then you finish, that is, you push the stop button on the same stopwatch, on 1 clock. So the proper time duration is measured by a single clock. The way that I know that in this earlier analysis, so in O prime, that's where the time delta t prime is measured. And the reason that I can say that it's measured by 1 clock is because it's this particular detector that is also a timer. And it is this single timer that's measuring the amount of time, the time duration, between the emission and then the detection. It's 1 clock. So over here you might say, well, what about delta t? It must be associated with this moving clock instead. And the answer is no, actually, that's not the right way to look at what's going on in O. So let me show you what happens in O. So O, this is observer frame O, and let's say that this is the x-axis. So let's say that this is x1, this is the position at which we get the emission, right? This is the position of the emission, and then it travels over, right? Just as referencing this picture from earlier, the emission happens. At a little bit of a distance down the line in O is the reflection, and then the same distance again is when in O, or I mean where, the detection happens. So that's the emission, and here is, let's say this is a second position where the detection happens. And the point is, so here is the light going into the detector. So this is, say, source and detection. Do you remember when we have an omnipresent and omniscient, omniscient observer, O, has an infinite number of detectors. So this detector is not actually, it doesn't actually belong to O. These detectors here and the source itself actually in some sense belongs to O prime. So this is a detector that belongs in O prime because this detector is standing still in O prime. But, so this is really a detector D prime, right? And this is the source S prime, say. And the detection in O happens with one of O's detectors that has a clock. And this detection, this is the detection in O with a completely different clock. These two clocks are separated in distance. So this would be like clock number 1, and this is clock number 2. So in O, you have to use 2 different clocks. And this is the difference. But in O prime, this light clock is actually at rest in O prime. So the detector that you're using to detect the emission and also the detection at those 2 different moments in time, those 2 different moments in time can be measured against a single clock in O prime because detection and emission happen at the same place. So now we're going to try a different thought experiment. In this case, we're going to turn the light clock. And the idea is we're earlier, the orientation of our light clock in our thought experiment was transverse to the relative motion between O and O prime. in this case, we're going to imagine taking this light clock and turning it this way so that it travels sideways. That is, the light clock moves such that the light travels purely along or parallel with the direction that O prime moves in O, or that O moves in O prime, honestly, because it's purely just a relative motion. Okay, but the light clock is still stationary in O prime. So in O prime, we have this light clock, and you'll notice that very carefully I designated the length of the light clock, or the distance between the source detector timer and the mirror, as L prime in O prime. But in O, the length is, I can't think of it as having the same length. I'm going to show you that in fact it has a different length. So it's L as measured by O. But it's the same light clock, right? This particular light clock is stationary in O prime, but this particular light clock at different times, right, is at different locations. Okay, so the way this analysis goes, or this thought experiment, is we just follow our nose for a minute. So easy thing to write down here is the amount of time it takes for a little photon or little small segment of light to travel across, reflect, and then go back. And that amount of time is the distance traveled, which is twice L prime, divided by the speed it travels it at the speed of light. So I've got this. And I'll notice very quickly, this is the proper time, right? It's not a bad idea to go ahead, like any time that you have a homework problem or you're trying to follow an example described in a book or something, you should attempt first that if there is a time revealed to you, like an amount of time, ask yourself if it's the proper time. And if it is, I think you should make a note of it. If a certain amount of time is not the proper time, you should make a note of that as well. Just say not the proper time. In fact, I'm going to show you over here, we're going to calculate up an amount of time, and it is not the proper time in O, what I'm going to show you, that we're going to do a thought experiment for. So to get from, so the light clock in O is traveling towards the right at a speed u, right? So on the side we have a relative speed of the observers, still called u. Okay, so here is the event of the emission of the photon, and here is the event of the reflection. So this is the reflection event. And up here, this is the emission event. And the amount of time as measured by O is, let's say it's called a delta T1. And then there is another amount of time. The amount of time it takes to get from the reflection event to the detection event. And this amount of time is called delta T2. And there is a total amount of time as measured by O between emission and detection, which is simply the sum of the two times, delta T1 plus delta T2. So, for example, delta T1 is equal to, it's the, distance traveled divided by the speed used to travel the distance. And what's interesting is you'll notice that the distance is from the emission location in O to the reflection location in O. So once the signal is emitted. The problem is the apparatus itself follows the emission of the signal, so that the distance traveled is actually longer than L. And in fact, what you would say is that the distance traveled was L plus, in this amount of time, the apparatus traveled sideways at a speed u, right? That's the speed of the apparatus in O. That's the speed, actually, of the mirror in O. So that's the distance traveled during this first delta t1. So you can see that the amount of time actually depends on itself. But you know how to do algebra, so you can just simply solve for delta t1, right? And what you get is, well, actually, I won't go that far. I'll go on and list how you're going to determine the amount of time it takes from the reflection back to the detector. So again, this is the distance traveled divided by speed. And in this case, instead of having to travel a larger distance than L, because the reflected beam is headed back towards the detector that's catching up to it or advancing towards it, then this distance is smaller than L. So it's smaller than L by the speed u, that's the speed at which the detector comes up towards the photon, multiplied by the amount of time it takes, to cross back, right? Delta T2, it's from the reflection back to the detection. And of course it happens at the speed c. So what's interesting about this is these delta t's, right, are the two parts of of delta t, the total time from emission all the way to detection, and depends on L, right? Over here, this delta t prime depends on L prime. Right? So this delta t prime depends on that L prime. But what I want is a relationship. So I want to, so the goal is to relate L prime and L. And in order to do this, I have to use, so I must use relationship between delta t prime and delta t, right? This relationship is from a time dilation relationship, and I noted over here that delta t prime was actually the proper time. So what you'll say is that the relationship between delta t and delta t prime is a time dilation relationship, so delta t is 1 over the square root, 1 minus u squared over c squared, right? That's all in the square root together, multiplied by delta t prime. So if I know this relationship between delta t and delta t prime, then what that can give me is ultimately a relationship between L prime and L. So when you go through all of that stuff, you get, right, so do some algebra, and you'll get the relationship the relationship between the length L and the length L prime is got the square root 1 minus u squared over c squared on top with L prime. This is different, so this is called the length contraction formula. So this is the big deal here. And you can see that actually it looks a little different than the time dilation formula. The time dilation formula from earlier is this relationship. You can see that, so this is delta t measured in O. This is delta t prime measured in O prime. And the relationship between them is a 1 over the square root. It's called the time dilation formula. Over here, this says that the length measured in O and the length measured in O prime are related by not 1 over the square root, but instead the square root just on top. And this is called the length contraction formula. So up here, the idea is moving clocks run slow. This is time dilation. This is the sort of mnemonic device for the phenomenon. The phenomenon is a moving clock ticks away its seconds slowly. Over here, the idea is a moving ruler will be measured to be short or contracted. This is so contracted means shortened or contracted. Contraction is to pull, to make smaller. Okay. Yeah, so this is length contraction. This is length contraction. This thing right here is time dilation. Yeah, so an important point to point out now is since, so this is a big note, since the light clock is stationary in observer frame O prime, then L prime is so-called the proper length. Right? The light clock is stationary in O prime, so the size of the light clock is the proper length. Just like, let's see, I wrote it up here. Delta t prime was what's called the proper time because delta t prime is reported by a single clock. And the reason that it's reported by a single clock is because delta t prime is measured by a timer that stands still in O prime. Right? If it stands still, then you don't need another clock. You can just use the same clock again. Up here, all of the object is standing still in O prime, right? All of our light clock, that is the detector, timer, and mirror, this object is at rest in O prime. So this length L prime, as measured by O prime, it is the, proper length. So this is the idea of the proper length. Oops, I wrote some stuff you can't even see. Let me push this back up here. So I think you saw me draw this. This is just another picture of the light clock. And I'm saying that since the light clock is stationary in O prime, when the observer O prime measures the length, because it's measuring a length that's stationary in its frame, that length is called proper. So to finish off this video, I want to talk about something it's a function called gamma. That shows up a lot in special relativity. So some books point out the importance of the function more than others, but I think it's nice to point out the function called gamma. So the way we'll define gamma, so we'll just define this thing called the gamma factor. It's a function of speed, and sometimes you'll use it to be the relative speed between frames, which is how you've seen it so far in this lecture. Sometimes it's just a function of the speed of an object in some frame. But yeah, so we'll just write it as gamma of u, and it is 1 over the square root of 1 minus u squared over c squared. So this is the gamma factor. Another way you might see this written is just with a slightly different, math representation or something, but it's also, you could write it this way. So instead of an explicit square root symbol, you see a exponent to the half, and instead of 1 over, you see a minus exponent, right? So it's all the same kind of thing. Time dilation says that, excuse me for doing this, I just don't want to make the mistake. So delta t is gamma of u times delta t prime. This is the statement of time dilation, where delta t prime necessarily is the proper time. And length contraction goes the other way. That is, the length measured by observer frame O is equal to 1 divided by gamma of u times the proper length as measured by observer frame O prime. So L prime is the proper length measured in the rest frame of the object. All right, so gamma of u, let's look at gamma of u. So inspect gamma of u. So if I was to look at this, and it's like, okay, so interesting. It's a function of u. It's got the c squared underneath the u, and so it's dimensionless. And so 1 divided by the square root of 1 minus something that's always positive. So I'll be going 1 divided by something always less than 1, if you think about it. So gamma, since it's 1 divided by something less than 1, gamma will be bigger than 1, usually. So if we inspect this, we can say that gamma of u will always be bigger than or equal to 1, right? Gamma of 0 is equal to 1. And gamma of speeds u that are not 0 are bigger than 1. So if there is no relative speed between O and O prime, then O measures delta t equal to 1 times the measurement of time by O prime, right? So there is no difference. That's what that says. And the length contraction is the same, 1 over 1, right? The lengths will be measured the same if there is no relative speed. But if there is a relative speed, then gamma is going to be bigger than 1. That is, the amount of time as measured by O is going to be bigger than the amount of time as measured by O prime. So you could say that delta t, measured by O, is always going to be bigger than or equal to the proper time. This is the time dilation statement. Here, L will always be less than or equal to L prime, right? So the observation in O is that the length seems small, is the idea. That's the length contraction. Furthermore, you can draw, right? Or actually, instead of draw, let's put graph. So let's graph gamma. So the relative speed, it's only important to study u being bigger than 0. So this is u, and we don't need to draw the negative values of u. So just the positive values of u, and this is gamma of u. And it's interesting, when u equals to 0, I get the value 1. And then when u is not 0, gamma is bigger than 1. And the way it increases is interesting. So it's going to increase, and it turns out it kind of increases in this curve, but there is a particularly special value of u, that's c. So if when u equals to c, so gamma of u equal to c, this is positive infinity. So what we have is an asymptote. Right? So, yeah, so this is kind of like, mathematicians don't like this. You could say that the limit as u approaches c from the negative side of gamma of u is equal to infinity, or something like that, right? Yeah, but this is a picture of gamma, so a graph of gamma.